Hello, welcome to today's seminar. At earlier time, our speaker today is Alex. Yes, please. And he will be speaking about partitioning random graphs with Turán graphs. So, talk with
What should I be doing?
The dark in front of the.
Right.
There we go. Perfect.
Yay!
Okay, great. Thanks, Bernard, for the intro. As you can see, I am recycling some slides from a talk I gave at the Rainey Institute in December when I visited there. So this talk is actually tailored for a larger time frame, so I might skip a proof or two in the middle of it. But
skip a slide.
6 slides.
thanks. This is a compilation error, so ignore that. So I'll start with sort of a famous area of motivation, which is a famous theorem of Bollobás in 1987. The theorem states that if you generate a random graph with density p, then almost surely we know exactly, up to some error, what its chromatic number is. So does anyone not know what GNP is here, what I'm writing here?
No, I don't know what that is.
Okay, so basically put n vertices in a pile, and for each edge, for each possible edge, like every distinct pair of vertices, decide with probability p whether you add an edge in or not.
Okay.
And do that independently for all the pairs. Okay. So that the roughly p proportion of the edges should be present, and so on and so forth. So here the chromatic number depends, as this is an asymptotic statement that I'm saying almost surely there exists a small range of values centered around this value, for which that's the chromatic number. And you'll see that there's this dependency on p. The base of the logarithm varies with how p varies. So if p is large, then you have a dense graph, and its chromatic number should be higher. If you have a sparse graph, its chromatic number should be lower. And that's reflected in the monotonicity of that value. There's another notion called a co-chromatic number, where your graph is allowed to be decomposed not only into independent sets, but cliques. And a similar result holds that the co-chromatic number is the same kind of expression, except the base is variable in this sense. So for example, if your graph is dense, you should be biased towards decomposing it with cliques. So if p is greater than a half, this value dominates. And otherwise, the graph is a little sparser, so you should be using independent sets to decompose the graph.
So just for the definition, it means that either all the sets in the decomposition are independent or all the sets are clique?
You're allowed to use a mixture. So you could say clique, clique, independent set, and so on. Yeah, any other questions about that? So that's just a baseline of motivation for this. I'm going to come at a motivation from a different direction now. And we'll eventually see that they reach the same point, but I just wanted to start with the most prominent result. So in 2008, Noga Alon and Yuri Stav asked the following question. There are a few other researchers involved in that. But the question is, what is the graph that is furthest from a hereditary property? And if you haven't seen these two words, a hereditary property is a graph class which is closed under relabeling the vertices, which is to say, call the vertex U, now call it Batman or something like that, and vertex deletion. So you can take induced subgraphs by plucking out all vertices and incident edges, and that would be called a hereditary property if it's closed under those two operations. A bit of ideology is implicit in the statement that all interesting graphs are hereditary. All interesting graph properties are hereditary, although there are a few examples, right? The property of being Hamiltonian is not hereditary, for example. But some examples of that would be planar graphs. If you take a planar graph and delete vertices, it's still planar. Being bipartite or two-colorable is hereditary. There are lots of famous hereditary properties, and we'll go through some examples later. And what do I mean by furthest? So if we're talking about two things being far away from each other, we need to know what distance we're using here. So we're going to use for the rest of this talk the edit distance, which is the number of edits to the edge set needed to transform a graph into another. So I'll take this example over here. which is a graph on 4 vertices and another graph on the 4 same vertices. And let's look at how many edits you need to turn one into the other. Well, this triangle is present here, but it's missing here. So you would want to delete these edges and then, now these edges are present here, so you would need to add those 2 edges back in. So you get 1, 2, 3, 4, 5 edits to turn that into the other.
I see just one edit, you can remove an edge.
So you're using graphs up to isomorphism. So we'll start with it being for labeled graphs, but you can, if you wanted to, allow yourself to permute the
Oh,
vertices.
so the vertices are labeled and they are ordered exactly the
Yes.
same way?
Yes.
I see.
Yeah. So if the graphs do in fact have the same vertex set, then you would want to normalize by n choose 2. The reason for that is a complete graph is n choose 2 edges away from an empty graph on the same vertex set. And this is just a fancy way of saying the symmetric difference, so edges in common in one but not the other. And so this normalization allows you to put the number between 0 and 1. And the goal for that is roughly so that we can compare distances in graphs between different numbers of vertices. So naturally we'll take n to infinity later. So their question, more formally, is given a hereditary graph property, what is the value of this limit? And this is a little bit of abusive notation too, but what I mean is the distance from this graph to any representative of this set. So it would be a minimum implicit inside this formula.
So now you remove the labeling?
That would be implicit in how this is done, yes. Because you would take the nearest graph, and it would be close to something that's on the same vertex set. Yeah, and it's actually not even clear that this is a well-defined limit. Maybe technically you should put in a lim sup before. But we'll see. I'll claim for now and not show that this actually does exist. So let's go through a couple examples because maybe this is a little too abstract and nonsense. So what's the furthest graph from being bipartite? Who has a guess for the least bipartite graph?
Okay.
Yeah, seems like or empty graphs are bipartite. If by bipartite I mean two colorable. So Kn, and it requires about n choose 2 over 2 edits. Because the densest bipartite graph is Kn or Kn over 2n over 2. The furthest from being a planar graph, well, planar graphs are generally fairly sparse. So a complete graph is still pretty far away from this. So we see a pattern. Are all the furthest graphs complete? Well, okay, let's take the property of being complete. What's the furthest graph from being a complete graph? Empty. Okay, great. So again, it's still requiring these same kind of sort of straightforward to see constructions. Now I'm going to introduce this other notation. So we can generate, given a small graph, let's say cycle of length 4, we can generate a hereditary property based on it. So forb of C4 will be the property of avoiding as an induced subgraph a copy of C4. So a big graph H is C4 free if you can't pluck out vertices and be left with something that's exactly a C4. So what is the distance between, what's the furthest graph from being C4 free? That's actually non-trivial. What's that?
Is it
A cycle?
Complete bipartite graph?
yeah,
This many C4s.
the balanced? I would say the balanced complete bipartite graph would be a good guess.
Yeah, these are great guesses.
A cycle, big one?
We're actually going to find out. It's actually a random graph. So let's just talk for a second about how to make something forbid something else. So we have some maybe big graph G, and let's just assume it has a lot of C4s. Or not necessarily that it has a lot of C4s, but that they're hard to remove. So here's a stupid thing we could do. We could just delete all the edges, right? So now we've deleted all of the edges out of possibly a big graph with possibly many edges. But that does work as far as removing C4s. Another thing we could do is we could add in all the missing edges. So if you complete a graph, it's not going to have induced C4, because you'll have the x as well as the square. But sort of in this naive sense, what we now have is that for any graph, you can get an upper bound on its distance to form of C4 by what you would get from adding in, or deleting all the edges, and then what you would get from adding all the missing edges. And so for any graph, it's only half of the number of total possible edits needed to make it C4 free. And you can ask how optimal this is, how optimal this argument is. And hopefully it's not optimal, because otherwise we have a very boring question. Now, there's another pile of constructions of C4 free graphs other than complete and empty graphs. A split graph is a graph which can be decomposed into a clique on one side and an independent set on the other, with who knows what else in between. You can tell that this is C4 free by the following. Well, where would you put a C4 in a construction like this? You would either have 2 on one side and 2 on the other, 4 on one side, 0 on the other, or 1 on one side, 3 on the other. And you can tell by inspection that none of that is possible, because as soon as you put 3 on one side, you get a clique, and triangles, or anti-triangles can't exist. And then analysis follows for the other cases. So I'll just sort of summarize this structure in the following fashion with this nice little untixy drawing made by hand. So if I were to visualize this as a kind of abstract structure, you have a cliquey thing on one side and an independent thing on the other side, and just kind of gray matter in between. We don't really know what's going on here. We don't necessarily assume. But anything that looks like this is going to be C4 free. So if we wanted to transform a graph into something like this, that would be sufficient to make it C4 free.
But B1 and B2 have all the vertices. There's
Yes,
no edges between
yes, exactly. So we're going to, for now, we'll call this a graph template. And let me describe how we can use this graph template to transform other graphs into being C4 free. So start with any graph. Randomly partition its vertex set. And we can just say uniformly at random. So put things on the left with probability 1/2 and on the right otherwise. Now what we're going to do is fill in the graph on the left, make it complete, and empty the graph on the right. So now the graph will in fact resemble that structure. Don't do anything to the middle, by the way. Leave it. Because that's going to cost you extra work, right? And we're trying to do the least amount of work to kill all the C4s. So how many edges did we start with? E of G. And what work did it take to complete the graph on the left? Well, we don't know exactly. But what we do know is that at the end of that, about n²/8 edges need to be in this pile. And since we did this kind of randomly, you can check, using linearity of expectation, that about 1/4 of the big graph G's edges should have fell into this pile, right? 1/4 should fall here, 1/4 should fall here, and 1/2 should fall between in terms of edges, if this is sufficiently random in this sense. So the number of edits that you need to make is something like this expression, and there is in fact a concentration on that value. And emptying does the same amount of work. So about 1/4 of the edges fell here, and so you need to scrap about 1/4 of the edges. And we didn't do anything to the middle, because we didn't need to. So anyone have questions about that? Okay, so altogether, if we add these numbers together, you get something like n²/8 edits needed to be made. And again, by concentration of both of those, there's concentration down there as well. And it's kind of nice that there was a lot of cancellation. If there's a lot of cancellation, it sort of tells you that maybe you did something correct. And it turns out that this is in fact optimal. So maybe the other constructions that people were throwing out do in fact work, like complete by partite. But the distance, if you just used a random graph of density 1/2 and did this algorithm, that's the best you can really expect to get away with. So the furthest graph from being C4 free is asymptotically a random graph of density 1/2. So pretty much most graphs are the furthest from being C4 free, and that should be a confusing paradox to think about. Yeah, the shape of the graph, the space of graphs on order n it's confusing. It's very unintuitive. So let me formalize this notion of what this graph template is.
So you don't have stability, kind of, that you have this random graph, you have the complete bipartite graph, which is very not random.
I can show you where stability comes into play on a later slide, but there is stability.
There is.
Yeah. Okay, so to formalize this graph template idea, what I'm going to do is define a colored regularity graph. And maybe if you've been to Ryan Talks, you've seen this, and it's going to bore you, or maybe it's new and it'll go over your head or be too confusing and abstract. But let's do our best. So a colored regularity graph, which I'll abbreviate CRG, it's trademarked, is a complete graph on some maybe small number of vertices. But it's going to be endowed with a vertex partition. So its vertices here are going to be black vertices, and over here its vertices are white. And when you see black here, you should think complete, and when you see white here, you should think empty. Its edges are also going to be partitioned. But like in the previous example, we needed a notion of edges that maybe aren't completed or emptied. So we're going to keep black, white, as well as add some kind of gray area. Gray will generally mean it doesn't really matter, don't bother changing it, it doesn't do anything for you if you delete or add. And how exactly are we going to apply this? Well, a CRG is kind of a graph template, and we're talking about forbidding small graphs, so we need to come up with a definition of how we embed small graphs into these graph templates first off. So an embedding of a small ordinary graph into a CRG is a function on their vertex sets, which map G edges into black vertices, black edges, or gray edges. So you can map two edges. You can map an edge in the small graph to the same vertex as long as it's black. And sort of the converse should also hold. A non-edge needs to map into a white vertex, a white edge, or a gray edge. So that's the notion of embedding. And if you've seen regularity lemma and if you've seen embedding lemma, this is the same notion. If you draw out a regularity partition and make this kind of diagonal assumption that you have cliques and independent sets, and also no irregularity, which you never do, but if you get all these assumptions, this is the same notion as what it means for a regularity partition to admit a small graph with positive density. Okay, so what I've sort of intuitively outlined on the previous slides is that C4 doesn't embed into this CRG. So black vertex, white edge, or white vertex, and gray between. For the same reason that no matter how you map vertices into these clusters, not into clusters, but into these genuine CRG vertices, the function will fail to be an embedding. So we're only at 7 out of 6 slides. So a motivating result of Allen and Staub is that the same game holds. And what game are we playing? Well, let's start with, okay, this should be a non-trivial hereditary property. There exists a parameter between 0 and 1. And the furthest graph from that hereditary property is asymptotically going to be what you attain. There should be a limit here. Is asymptotically what you should obtain if you just took a random graph of that probability. So we saw in those previous examples that complete graphs and empty graphs can also show up. But a complete graph is just a random graph of density 1. And an empty graph is just a random graph of density 0. So this is consistent with all the other results we have so far, barring this limit that I failed to write down. So intuitively, the furthest graph from a hereditary property is random somehow. It's some kind of random graph. And what we're going to demonstrate on a later slide, this will be written as a theorem, is that more or less you should use colored regularity graphs that you can associate to a hereditary property. And in some sense, those colored regularity graphs will tell you what a typical element of the property looks like already, which means just use the template and find out the right way to compute distance to it. So let me describe roughly how we govern the distance between a random graph and a colored regularity graph. So we're just going to select an optimal weighting, and we'll figure out what optimal is later, of the vertices of the CRG. And those will be the biases with which we map the vertices of the random graph into. So I'm going to take a big random graph and a small CRG. The CRG has k vertices, and we've weighted them accordingly. And we're just going to come up with a random function from the vertices of the random graph to the vertices of the CRG. And the images of each vertex will be chosen in accordance to the weighting. So with probability xi, it will end up in vertex wi. And this selection will be done independently for all the vertices in the random graph. So it's a random process on a random graph into a structure that's not really a graph. Now, how do we make something resemble a CRG? Well, we need to abide by the same rules that we previously did. The CRGs are going to be graphs, are going to represent, for example, C4 free graphs or other elements of a hereditary property. And so we should make the random graph resemble it by completing everywhere that's black. And by this, I mean we're taking our random graph and then adding in all the edges between vertices that are sent to a black vertex or a black edge. So we are modifying the random graph.
So this is add an edge?
Into the random graph.
Because it's written non-edge.
Maybe it's at an edge.
Yeah, you're right, that is backwards, yeah. So you need to add the edge, if it's not already there, in the random graph. Thank you.
So it's a typo, the non-edge.
No, he's saying add UV that was a non-edge.
You're right, that
Oh, I
UV
see,
is a
I
non-edge,
see,
and
I
you
see.
add it.
if you send anything to black, then it should already be an edge. So we're going to make this function a homomorphic,
If
or
it
an
wasn't an
embedding.
edge, I did.
Yes, if it wasn't an edge, okay, I see, yes. Add the non-edge if this is black. Remove the edge if it's white. There we go. That's the way to fix that. The sentence was confusing. Okay, now there's this annoying expression that governs how much work you needed to do in expectation, right? So 1 minus p means you're adding missing edges in a cluster that originally had density p, and p means, well, I'm subtracting edges from a cluster that had roughly p proportion of the edges. And we're going to define gk of p for a CRG and just the parameter p, no dependence on the number of vertices at all, as the quantity that minimizes this expression, not maximize, minimize. And x will be considered an optimal vector, an optimal weighting, and so on, of the embedding of the random graph into the CRG. And so this sort of Franken theorem is a generalization of what Alon and Stav were doing. So we are actually going to vary the parameter p and ask the question, what graph of density p is furthest from a hereditary property? So basically group graphs according to their densities and then ask which graph in that pile is furthest from that hereditary property, and then draw this as a function of p. Some things need to go into making sure that this is a genuine function when you do take the limit. So it is part of this theorem that this limit does in fact exist. And it will look something like this. But in order to actually do computation, you need a result like this. So Allen and Stav proved that some random graph is the maximum. This part, which is the Marchant-Thomason part, showed that actually for every p, the random graph of density p is the maximizer among graphs of density p. And in order to actually compute that, you take the minimum over all CRGs associated to a hereditary property of that distance function, the g function, associated to that. Moreover, the function is actually continuous and concave down. That's a lot. That's a big mouthful.
The minim or minimizer.
The minimizer. I've never seen an example where there are multiple maximizers. Oh, the minimizer in this sense. So it's part of this theorem that this infimum is actually a minimum.
No, but didn't we have the thing that you have the complete bipartite graph for C4 and a random graph for C4? And so is it a minimizer or the minimizer?
Mm.
Because the theorem as written is saying a minimizer.
Right. There's probably just one. So there's this non-intuitive geometric result about the space of graphs, which says, roughly speaking, hereditary properties are the complements of a hereditary property is concave. And you also have to use a concavity result here, but the space of maximizers should also be a concave set. Yeah, that's easy to see. So it's probably not the case that there are multiple graphs unless the averaging between the two graphs is also optimal.
Okay.
And why do we even have a nice maximizer? Well, it's because this function of p, based on the hereditary property, is continuous and concave down. Continuous and concave down implies that there's a peak. I've never seen one where the peak is flat, and I don't think we've actually shown that there isn't a flatness that can occur. So we have these edit distance functions between interval 0, 1 and the interval 0, 1, and we now have sort of a general machinery for how to compute them. But let's do something kind of absurd. Let's generate a hereditary property based on a random graph. So generate a small but embiggening random graph, and generate the hereditary property based on forbidding that random graph. Okay. So more or less, you're going to pick a graph uniformly at random and allow the number of vertices to grow a little bit. And it turns out the edit distance function, if the graph is uniformly random, can be given by a formula here. And that's this result of Allen and Stav. The graph which is furthest from containing a uniformly random small graph is another uniformly random small graph. Big graph. Sorry, I should say big.
Is it different p maybe?
If it's uniformly random, it is the same p.
It's the same.
It's gn 1/2 avoids gn not 1/2. Think about where this peak is. The minimum of this is when p equals 1/2.
Okay.
Or the maximum of this expression is when p is 1/2. So our goal is actually to generalize this result. Vary the density of the random graph that you generate, and figure out what random graph is furthest from containing that random graph. I will probably skip this proof because I think we could use the time. Maybe I'll come back to it. It's on page 12 out of 6. But let me just quickly say what this has to do with the result I wrote out earlier about the chromatic number of a random graph. So if a graph can be colored with k colors in such a way that, you know, on those individual colors you have independent sets, then a proper coloring of a graph is actually an embedding into a CFG. So if your graph has a proper coloring, that looks something like this, right? And I'll use green for the color gray. If you've properly colored a graph, then you've embedded it into the CRG that looks like this, right? Because what have you done? You've mapped the vertices of that graph into a CRG with colors according to the number of vertices. So the reason why this formula holds is because implicitly you're using one of these kind of elementary CRGs associated to the chromatic number and the co-chromatic number, and then just editing away the edges that should or shouldn't be there. So it's not a coincidence that that 2 log base 2 term is kind of showing up, 2 being the appropriate base. So I will skip that, but that's the summary of that proof. And really, because of concavity, you only need to show equality at that peak if you show these upper bounds. So if your graph, if the graph in the Euclidean plane of the function is concave and you show upper bounds that are lines and you show the equality at the point at the top of the line, then equality more or less holds all the way. So we're going to try to generalize this. And what we do is the same kind of argument, but we don't have the same kind of technical lemmas about colored regularity graphs that kick in. And that's sort of the unfortunate area that we had to massage a lot to get around it. One thing I will say is, if you've never seen the result about the chromatic number of a random graph, then let me demonstrate why approximately it's true. So, let's see. Okay, so let's ask the question, what is the clique number of a random graph? Oops. Sorry, independence number of a random graph. Number of random graph. Let's say G and P. So what we're going to do is we're going to count the number of independent sets of order R, for example. So how do you do that? Well, you first need to choose all of the possible R-size subsets, and then you ask the question, what's the probability that those R vertices induce an independent set? So I've written out this kind of helpful combinatorial inequality. You could get better calculations if you use Stirling's number or Stirling approximation, but it doesn't improve the bound asymptotically, so we don't bother with that. And we're going to ask the question, at what value R in terms of N and P do you get about one independent set of size P, of size R? Okay. And that threshold after which you're getting more than one and getting less than one is close enough, and I'm talking a lot under the rug when I say that, it's close enough to the value that you get if you solve this equation. So let's try to solve this equation. What we do is, because of these upper and lower bounds, we're going to take the rth root of both sides. Okay, so on the left, we get n over r. And maybe there's a constant, right? There's a constant e that's snuck in here. Let's ignore it. And over here, we're taking the rth root of a power 2 r choose 2, so the r cancels away. And so we get 1 minus p to the r minus 1 over 2. And then we're saying that this is 1, but you know, we scrubbed away a constant, so maybe we'll say approximately 1. And well, I see one more constant that I'm going to kill, right? So r minus 1 is kind of annoying me, so I'm just going to kill that too. And well, we're trying to solve for r, I think. what I remember so far. So let's try to solve for r. Well, it's kind of complicated, right? So maybe we take a log. We could take a log base. Yeah, let's take a log base 1 over 1 minus p. Let's just take a normal log. So log, n minus log r. We're going to be dividing through over here. So now we have a log 1 over 1 minus p times r over 2. So what's the dominant term here in terms of r? The main term is this r over 2. This is kind of a tiny term, right? So if we want to know how big the independent sets are, we should solve for this r. Okay, let's solve for the r. And when we took the log, this became a 1 tilde. Trust me. So r is something like, what did we do? We multiply by 2 and divide by this. So we get 2, we should get a 2 over log 1 over 1 minus p on the expression log n minus log r. All right, we're trying to solve for r. Are we happy with that? No, because we've solved for r, but there's another r there, right? So we take this formula for r, and we plug it in for there. So okay, so now we have 2 over log 1 over 1 minus p of log n minus, well, our formula for r says log 2 over log 1 over 1 minus p times log n minus log r. And again, we have the same problem that we still have this r here. So I think we should go until we get rid of it, right? Or maybe that won't work. So I'm just going to kind of scrub this away. And what's the main term here? It's log n, right? Because r is the independence number of a big random graph. They shouldn't be close to each other. This term is basically nothing. So really, this is a log n, and this is a constant inside a log. So maybe you believe me that this is kind of like 2 log 1 over 1 minus p on log n minus log. Ignore this, log n. You don't have to believe me. You can choose not to. But that's how big independent sets in a random graph are. And so if the independent sets in a random graph are about this big, then you should use independent sets of about that size in order to properly color the graph, sort of by a really naive, greedy coloring of the graph. And there's a big theorem that backs that up. That's what Bollobás did. So we're trying to do the same thing for general random graphs. Where did the clicker go? Just running out of time. Let's see. So in order to kind of match the bound given by a random graph, or given by a naive proper coloring or proper co-coloring of a random graph, you need some sort of lemma. So what you do here is you say, well, let's maybe assume that I've gotten close enough to the edit distance function with some sort of CRG. And we're going to show that that CRG is pretty much the structure that you would get when you are properly coloring the graph or its complement. And there's a lot of junk going on here, but I need to move over here. I should have left that. So let me tell you what CRGs like this actually look like. So the optimal CRG K for forb G and not P naught is approximately the following. So you do have a couple cliques, and you might have a couple independent sets. Hopefully you have a lot of them, or hopefully you have a lot of those. But then there's these kind of annoying intermediate structures in between. And I should be saying that there's gray pretty much everywhere. And kind of between. And then there's going to be gray between structures like this, and then maybe some other structures. And let me tell you what those structures look like. And this may look nice at first, but it's not nice. Because the nice thing about embedding into structures like this is you could just do them one at a time. Put some of the vertices in this pile. You don't need to care about how they relate to anything else. Put some vertices in this clique. Don't care about the relation whatsoever, but maybe, and then it's all gray in between. But with a structure like this, you have clique structures with genuine emptiness between them. You can't assume that it's gray between these structures. And so the CRGs that we use aren't just these nice ideal CRGs. We have to allow ourselves to mix in these kinds of ugly structures. What are those structures in actuality? They're just blown up copies of a clique. So, let's see, I did that calculation. Let's see if I can demonstrate this here. Yeah, so imagine instead of looking for a clique inside a random graph or an independent set inside a random graph, what if you were actually looking for and we'll call this a Dalmatian set because it has spots, right? So and maybe we'll call that D of t or D sub t, who knows, inside random graph. Okay, so what I'm doing is I'm going to make some optimality assumptions. Let's say it has R vertices. And let's say I have T spots. I'm just going to use T as 3. So how big should a structure like this inside a random graph be? Well, let's count. How many structures like this should there be? I think it kind of behooves us to assume that these are all the same size. If they're not all the same size, then you should look for something else. But if they are the same size, then you're going to find not only more of them, but they're going to occur with higher probability under the right assumptions, which are in the background of all this. Okay. Am I going to? So there are R over 3 vertices here. R over 3 vertices here, and R over 3 vertices here. How do we find a potential candidate for a structure like this in a random graph? Well, we're going to first pick R vertices. And then among those R vertices, we're going to break it into 3 equally sized pieces. R, and if you've seen multinomial coefficients, they're just the products of the corresponding binomial coefficients, but this is to represent an ordered partition of an R-sized vertex set into 3 R over 3 sized classes. There's floors and ceilings everywhere, but we're ignoring all of that. And R is replaced by T, but we're ignoring that. And we want cliques inside the clusters and independents everywhere else. So I'm running out of space here, but P should be raised to some power representing the edges inside the cliques. and 1 minus p should be representing the edges within the pieces, or between the cliques. And what we do is we solve that same exact equation and we get a guess. Okay, but we don't have Bollobás's result. We don't have Bollobás's result a priori, at least, because we would need to actually genuinely be able to find lots of structures of the biggest possible size over and over and over till we decompose the random graph. In other words, we need a concentration result. And that's what we should. A corollary of that is, in the domain that we're working in, the edit distance function is asymptotically what it should be, which is what you would get if you were to genuinely decompose into either cliques or independent sets. However, there's a domain where this is not necessarily true. We believe quite strongly that the actual constructions, the actual optimal CRGs, are precisely a pile of cliques or a pile of black vertices or a pile of white vertices. But that's still open. And not long after proving that, we actually found this other result of Bollobás, which it sort of subsumes this result. It's much, much wider spread. But it basically gives you a chromatic number of random graphs where instead of partitioning into cliques or independent sets, you're partitioning into elements of a hereditary property. So now things have gone in a complete circle where we're starting with a hereditary property about a forbidding and induced random subgraph, and we're looking to decompose the random subgraph that's furthest away from that property, and we use representatives. And the associated CRGs are bunches of piles of Dalmatian sets, and then we use the property of being a Dalmatian set with T parts as the hereditary property. So we can actually also get this as a corollary of Bollobás and Thomason. What I will say is that the Bollobás-Thomason result doesn't give you this theorem for all values of p. It only gives it for a certain range of p. So their theorem is more general, but in the precise region we get tighter results, the region of Dalmatian sets. Okay. I guess I should have, yeah, that's there. It remains to be seen how we can improve this bound. There's a symmetry argument that tells you only look for p less than a half, but we also don't know whether Dalmatian subsets of random graphs, whether you get the same kind of concentration result if you allow the number of parts of the Dalmatian set to grow as a function of n. So if the number of parts here is constant, then we have our concentration theorem. That's for any p and for any fixed t. However, if the number of parts in the Dalmatian set grows, your graph is looking a lot cliqueier, or a lot more independent, and you would expect the size of that to resemble the independence number, which it should, but we don't know whether we get the same confidence level if the number of parts in the Dalmatian set is growing. Okay, that is the talk. Okay. Any questions?
So I'm guessing the answer to this is no, but is there a CRG, is there a finite CRG for which every graph can embed into?
Hopefully not. Yeah, I don't think that's true. So
If you allow gray vertex, if you allow gray vertex.
and then if there's a gray vertex, then everything embeds into it. I think as long as you step over the chromatic number of a graph, like if the CRG has fewer white vertices plus black vertices than the co-chromatic number of the graph, then you can't fit the graph into it. So I think, yeah. The answer should be no, and I think that's a reason why. Oh, and I never explained gray vertices, did I?
You didn't mention that they are allowed.
I said they're not allowed, and the reason why they're not allowed is hereditary properties shouldn't have gray vertices, because if you have a gray vertex in a hereditary property, that's kind of like saying that you have a random subset, a random subgraph, and random subgraphs contain everything, so they shouldn't be found at all inside hereditary properties.
Just curious how the 0.4402 what fails.
So that number is actually a lie. We did a miscalculation for it. It's actually closer to 0.38. So the structure lemma has some assumption that, like, I think p squared minus 3p has to be greater than or equal to 1 or something like that has to hold. So it's a quadratic equation.
If you say 3.8 instead of 4.4, then the 4.4 is still correct.
The 4.4 is still correct, but
But you can do
0.38 is
better.
actually accurate. Yeah.
Okay.
All right, thank you all.
Thank you.